we are moving to the next one, and I would like to invite Sunniva Rose to present her speech. Just a reminder, we have 20 minutes speech and 5 minutes questions. It's on?
Yeah.
Okay. Well, I'm Sunniva Rose, and I come from the University of Oslo. I'm a PhD student there, and at the SAFE Center, which is the Center, a Norwegian acronym for the Center of Accelerator-Based Research and Energy Physics. And I also work with John Wilson, who is here, who comes from the IPNRC outside of Paris, which is a CNRS lab where they and they have interested in do research on thorium. So that's why we sort of have a common interest there. And I'm now going to talk about the potential use of thorium-based fuels in existing reactor designs. So it's not really generation 4, I'm sorry about that, but it's, let's say, a 3+, just before generation 4. Okay. So the background is that there is an expansion of nuclear, also after the Fukushima accident, I think. And if you continue then with mostly once through cycle with uranium, the easily extractable uranium sources will become depleted, which will lead to higher uranium prices and also large quantities of waste. So we need strategies that economize on uranium resources and help solve the waste problem, and this via reducing waste inventories, which is of course also what generation 4 aims to do, but it's a bit farther into the future. Okay, so why thorium? Well, as we all know, thorium is a fertile material and changes into uranium-233, like uranium-238 changes into plutonium-239. But thorium is actually an excellent, fertile material because it has a higher eta, which is the neutrons emitted per neutron absorbed, than plutonium-239, which means that a new fissile material will always be greater than with uranium-238. It also has a capture to fission ratio, or uranium-233 has a capture to fission ratio alpha, which is lower than for plutonium-239. And this means that the waste production will always be smaller with thorium fuels than with uranium fuels. And this, we like this, that's nice. Okay, so if you see a bit about the neutron budget for thorium-232 and uranium-233 fuels, this is what we see, sort of the neutrons per fission here, and of course you have one neutron that actually drives the chain reaction. So these are what we're left with, because since we have more than 2 neutrons per fission, in principle, we should be able to breathe. But then, if you see here the spectral hardness here, if you're at the thermal energy range here, what happens to the neutrons? Well, we have quite a lot of capture on the hydrogen in the water. So what we could do is that we could change the water with heavy water, H2O, which is what you do in the Candle reactor. The problem is that you will only have short burn-ups, which is not very economically. Then in the epithermal range here, you don't have so much capture on the water, but you have a lot of capture on the fission products. So you could, of course, then get rid of the fission products, which is the concept of the molten salt reactor, to remove the fission products online. Problem is that it's a difficult technology, at least not today yet. And of course you could move into the fast neutron structure. the problem, or not problem, but we don't have an inventory of uranium-233. So uranium-plutonium fuels would definitely have, or be better probably for fast-breed reactors, since we already have a lot of plutonium already made. And also because, well, these changes when we go into the fast emission range. So plutonium is probably better for fast-breed reactors. Okay, so of course the ideal goal is the self-sustaining thorium cycle. And when it comes to thorium, we have generation 4, we have the thorium molten salt reactor, and where we remove the neutron poisons online, and the accelerator-driven system where we add an external neutron source. But this is, well, we say this is far into the future. It's nothing that we can do today. It involves more research and development. Then we can be able to demonstrate it before we could build the prototype, and then we could do it like for real. So the self-sustaining thorium uranium-233 cycle is possible, but it is way into the future. And so we wanted to do more research into thorium in existing designs, which is cheaper than dedicated designs, and it can be deployed quickly, which we think is interesting. So the disadvantage is that self-sustaining is not possible, and the cycle is dependent on existing uranium-plutonium cycle, since we will need, well, for example, high-energy uranium as a neutron source. So how do we do this? What did we do? Well, we used the program called MUL, which stands for MSMP Utilities for Reactor Evolution, which has been developed at the IPN of SE and the LPSC of Grenoble. And it is Monte Carlo-based precision research code, and it's very well adapted for innovative system and fuels. And it's an open source available at NEA. Okay, so this is the first approach that we did. We looked at this minimization of actinide waste by multi-recycling of thorium-based fuels in the EPR reactor. And this was to examine thoriated fuels as an alternative to the present MOX recycled fuels. And we wanted to provide greater uranium resources and lower waste inventories. So this was sort of, what to say, we looked at the homogeneous first step, a homogeneous fuel, homogeneous core, nothing very advanced in a way. So, but we did multi-recycling. So we studied, as I say, homogeneous fuel in the EPR at a 65 gigawatt days per ton burn-up. Then we cooled it for 5 years before we recycled the uranium and thorium. And then, to make the new thorium fuels, we recovered the uranium, the entire uranium vector, of course. And we also had to add some freshly enriched uranium. So high-enriched uranium was the neutron source for this fuel. And the reason why we had to add extra enriched uranium is because we're not breeding, it's not self-sustaining. And then we did this again and again. So with the recovery of plutonium and making MOX fuels, you only recycle once, right? And this was multi-recycling, we did it again and again. And what we saw that with this thoriated fuels, initially it costed a lot with separated work units and enrichment work. And also more natural uranium, since we had to enrich the uranium to a very high degree of uranium-235. But this investment was repaid when we reprocessed the fuel, since the uranium that we recycle is, has a lot of uranium-233 and uranium-235 that would normally just be waste. So just to go a bit more details about the fuels, we look at two innovative fuels that we call S20 and S90, and then we compare them with UOX and MOX fuel. And well, the UOX fuel is about 4% uranium-235, and we see it here. So the uranium-235 is the pink over here, and then the rest is of course uranium-238. And then the S20, which is then thorium here in the brown, and uranium that was enriched up to 20% uranium-235. And then the S90, which would probably not be allowed to do, but we're still interesting to study. Most of it is thorium, and the uranium content here is 90% enriched. So you can't even see that it's, of course, some uranium-238 here, but it's very, very small. So you see that these three different fuels, they contain similar but not identical amounts of uranium-235, but it's highly enriched when it's mixed with thorium. And what we saw then, I just show here the uranium vector of the S90. So it's inventory, core inventory of uranium isotopes as a function of burnup. So of course, when we start up, we don't have any uranium-233 or any recycled fuel. So then we have to, of course, add uranium-235 here. And then, as the fuel is in the reactor, the inventory of uranium-233 grows in, and then when we recycle, we have to add some uranium-235, but a lot less. And actually, we have a 50% reduction in the natural, or the needs of natural uranium. And but unfortunately, the uranium-233 stabilizes quite quickly at 2.2 tons, so it doesn't continue to grow. So, and then the radiotoxicity of this recycled fuel is quite nice. It's I'm showing now both the S90 and S20, yes, and the S90 is of course the best result because it contains almost no uranium-238 to begin with, so it's produced very little transuranium elements. And you see after 1,000 years, it's actually 20 times less active than once through cycled UOX or UOX-MOX case. The S20 is not as good as the S90. It's about 1/3, which is still good. Normally, if you say that it's a 2/3 reduction, it's not bad, but not that good. Okay, so this is sort of a general, what to say? The case that I talked about now was a special case of this more general scheme of thorium and a multi-component fleet, because you could of course do better than just multi-recycling and doing it in the EPR. So here you have one reactor that would produce uranium-233, and then you had one reactor that consumed the uranium-233. And if you have a low conversion ratio consumer, then you would have to have a high conversion ratio producer here, and the waste would be quite high here, and you wouldn't, you're quite away from breeding. And then, if you have a high consumer conversion ratio here, this waste is this is much smaller than this one, and when this goes to 0, then you're breeding. So it's sort of a multi-component fleet to optimize on the production of uranium-233 here. And if you have more questions about this, then you should ask John here. Okay, and then a special case again here with you have this 3-component fleet. You have a pressurized water reactor that is on UOX, and you produce plutonium, and then you put the plutonium into the boiling water reactor to produce the uranium-233 that you put into the heavy water reactor where you consume the uranium-233. So this was also existing designs and water coolants, and it was a very high collective breeding ratio of 0.9. Breeding is still not possible, but we're getting close. And the fissile content is also here less than 6%, so it's proliferation resistant. And it's 50 to 80% economy of the uranium resources compared to normal once-through cycle, and reduction in the minor actinide waste will be the same or similar to that. Okay, so some general conclusions on safety. For example, when we're dealing with uranium-233, the delayed neutron fraction of uranium-233 is lower than that of uranium-235, and similar to plutonium-239. When we look at the EPR, so this is more general for the EPR reactor, it's designed for 100% MOX core. So in principle, it should be also able to have 100% thorium-uranium-233 MOX core. At the void coefficient, thorium fuels are actually better, and then we have the 233 platinum reactivity effect. And we saw that there's only need for 10% of the control rod, so there's no extra problem there either. The xenon samarium poisoning is similar to UOX, and the fuel temperature coefficients are also similar to UOX, so it's like no extra problem there. So, some general conclusions for thorium-uranium-233 consumers. You have the pressurized water reactor, boiling water reactor, CANDU, and they all have mostly advantages, but they all have one major disadvantage. For the PWR, you would have a large deficit of uranium-233 at each refueling, so the conversion ratio is not very good. For the BWR, it takes a long time to produce the high uranium-233 cycle inventory, which is not good. The CANDU reactor requires frequent reprocessing since they have short burn-up, so it's or it's expensive. Okay, this is the last part. Now we sort of changed it from reactor simulations. And well, reactor simulations are nice, but they rely on some nuclear data. And if you don't have good nuclear data, well then the simulations cannot be better than the data that they rely on. So my work is twofold. I work with the reactor simulations with John, and then I'm also in my PhD project will also do experiment at the Oslo Cyclotron laboratory, where we have a very good setup. We have this 64 charge particle detectors that we can measure charge particles in coincidence with gammas. So what we have started to do at the Oslo Cyclotron laboratory now is we're doing this indirect actinide cross-section measurements, which is called the surrogate method, and it's a very useful technique to measure nuclei where you can't measure them directly because they are very radioactive and have short half-lives. For example, uranium-232, which is very important nucleus when it comes to the thorium cycle. It's not produced in very large quantities, but it has a very penetrating 2.6 MeV gamma, so which makes reprocessed thorium fuels very, very difficult to handle. And also, there we don't really have very good knowledge of many of the cross sections there. So we will try to study this, which we do with this surrogate method or indirect measurement. So we, for example, put in the uranium-233 target, and then instead of measuring neutron capture, for example, directly, we can look at we can bombard it with deuterons, and then it will spit out the protons, and it will be like a surrogate for neutron capture. And these are some recent results. So here we see that, yes, there are big differences for the evaluated nuclear databases gives for the cross-sections here. So here you have all the different evaluated nuclear databases, and they don't really agree. And here are OCL results from indirect measurements on thorium targets. So see, there are still some work to be done here, which of course would affect the simulations that you do when this is the input. And then, the last slide now, level density bubbles are important for cross-section calculations, and this is also from the same experiment on thorium. So we see here when we come to them, well, they quite agree in the thermal energy range, but when we come to faster neutron spectrum, then they start to not agree at all. And these are results from the thorium experiment. So these nuclear level densities and gamma ray strange functions are being measured for actinic nuclei at the LCL, and they will allow a systematic understanding of these fundamental properties of actinic nuclei that are very important for these simulations. So then we could hopefully do better modeling of cross-sections where we don't have available data. So thank you for your attention. These are most of the, or some of the people of our collaboration. So thank you.
Thank you very much, Sunniva. Very interesting presentation.
Thank you.
And now we have time for questions, please.
Okay, so then it's
No
not.
question. I have.
Yeah, that's fine. I always have questions. You know, many people were trying in the past to think about this optimization of the thorium process, especially in India. And the showstopper always was the uranium-232, even if it's traces only, because it causes very hard gamma emitters.
Yes.
And also proof fabrication is very difficult then.
Yes.
In this case, the kjernereaktor has a huge advantage, and you did not mention that, probably should add it, because the fuel assemblies are very small,
Yeah.
and they're transported anyway, fully remote control to the
Yeah.
reactor and back again. So that means the country is better prepared for really complex, massive shielding than the PWR, where you take out the assemblies and you store them somewhere in the reactor. They're not prepared for such shielding there. That's why I think the country has the best.
Yeah,
Sure.
well, that's interesting. Yeah,
Yeah.
I agree.
But it's up to you to talk about that.
People, you mentioned the deficit of U-233 finally in the scenarios. And some people think to use actually the ADS to speed up the stockpile of creating the U-233.
We're thinking about that too.
Yeah, but I mean, you don't have numbers about that, or have you looked at what, for instance, Indians are doing, or Brazilians? There are studies going on that.
No, I guess we haven't done that, but we want to look a bit more into that with using the IDS to build up on the uranium-233. So we're talking about that.
India has a lot of experience, I guess.
Yeah.
I think the key designs of energy amplifiers based on thorium. If I read what people of English company proposing already for build.
I think the key question is how many ADS would you need to feed the deficit of a fleet of reactors running in sub-breeder
You
mode?
don't need any reactor. The concept is based to produce energy with energy amplifier, so with an ADS concept that seems to be workable and affordable.
We do have another question. Yes, please.
From your first part of the presentation about light water reactors in translational thorium, have you any figures to tell how much the prices of uranium should increase for thorium?
We have made some, well, it's difficult to make a very good estimate since there are uncertainties like how much would it really cost to reprocess the fuel, how much would it really cost to make new fuel. But we have made some first estimates about this. I don't remember the numbers now, but I can get them for you. We have a graph there where we see the uranium prices, and we come to like a crossing point where thorium-based fuels would actually be cheaper than uranium-based fuels. Yeah.
There is a break-even point when it becomes economical, and we're estimating this about $400–500 per kilo for a natural uranium price.
There are large uncertainties.
So yeah, there's large uncertainties in the reprocessing and fabrication costs. So there's a large uncertainty on this number, but at some point it makes sense to stop doing one through cycle and start doing the kind of thing that Sunniva's.
We would like these references in the report for line prepared.
Yeah, we can talk about that. Yeah.
Do we have more questions? Okay, if we don't have more questions, then I propose that we continue our session during the lunchtime. And I promise there will be the moderator. But thank you very much, Sunniva. It was a very good presentation. And if you are hungry, then we can go and have a lunch. If you're not, we can stay here and discuss.